Alright, for this video we're just going to do some example problems, but we're going to go back a little bit. We're going to be talking about mainly work energy with varying forces. We've done work energy before, that was the last chapter we did, but this time we're going to do some problems where the force is not constant, meaning it's changing. And an example is something that involves a changing force needed to exert some kind of work is mainly like springs and elastic material. And for that we're going to use Hooke's law, that says the force needed to stretch an elastic material is equal to some kind of force constant times the displacement from its natural position. And we'll be using this equation, and know that K depends on the material you're looking. So if you're looking like a slinky or a spring in your bed or any other type, or a rubber band, they all have different K's, but it stays constant as long as we're talking about the same material. So let's just quickly start looking at a problem. We have a problem here that it says a surgeon is using material from a donated heart to repair a patient's damaged aorta, so it's a vessel, and needs to know the elastic characteristics of this aorta material. Test performed on so they took a 16 centimeter strip of donated aorta revealed that it stretches 3.75 centimeters when a 1.5 Newton force pulls. Alright, so basically we have this aorta piece that is 16 centimeters long, and when a force of 1.5 newtons is exerted, it will stretch to a length of 3.75 centimeters. And then we'll stop. So the 1.5 newtons will stretch it as far as 3.75 centimeters. So because we're dealing with an elastic material, we're going to be trying to use Hooke's law. So again, Hooke's law is that equation that says F is equal to K times delta x, where K is the elastic force constant, delta x is how far it displacement from its natural length, and F is the force of the spring pushing back, trying to go back to its natural length. So when the person pushes with 1.5 newtons, the elasticity of this material is going to push back with 1.5 newtons. So if we set up our displacement in the x to be 3.75 centimeters, which we'll actually have to convert to meters later, and we set the force equal to 1.5 newtons, we can answer part A that says what is the force constant. So the force constant is the K, so we're trying to solve for K. So if we rearrange the equation, we find out that K is equal to the force exerted divided by the displacement that occurred because of that force. So we plug in our values and we find out that our K is 400 newtons per meter, and that's at 40 newtons per meter, excuse me, and that's the actual units for the constant, the force constant. It's always newtons per meter. That way when you multiply times your displacement in meters, you get newtons, which is what the force unit should be. For part B, they want to know what force is needed to stretch to 1.14 centimeters, which is probably what's going to be happening when the surgery occurs and it's inserted. So we use the same equation. We use the F equals K delta X. Since we already figured out the K in part A, and the K is dependent on the material, and we're still talking about the same material, we can use our K and just multiply by the displacement that's going to occur, making sure that it's in meters. And then we find out that the answer is 0.456 newtons. If the elastic material is going to be stretched by 1.14 centimeters, it would be experiencing a force of 0.456 newtons, which is really small, but this is like aorta. This is a small vessel in your body. Alright, for this next problem, we're actually going to have to use some calculus here, because we're talking about, it says to stretch a spring 3 centimeters from its unstrength length, 12 joules of work must be done. What is the force constant of this spring? So again, we're trying to find the force constant of this spring. And the information they gave us was a little bit different than before. They told us the displacement, but they told us that it needed 12 joules of work for this to occur. So now we're going to be dealing with work. So normally when we deal with work, we jump to our algebra equation. Our algebra equation, again, is the one that says work is equal to force times displacement cosine theta. But we can't use this equation because every little bit that the spring gets stretched out, the force needed to move it just a little further changes. So again, we have a force that's changing, so we can't use our algebra formula. We have to use our calculus formula. Now, our calculus formula says that work is equal to the integral of the force with respect to its displacement. we use x instead of r. R is the actual letter or value that are represented in the equation sheet, but r is meant to be for like the vector of the displacement in multiple directions. So when we're talking about moving in the x and y at the same time, we can't say x. But since this is a one-dimensional problem, because the string is not being stretched in all kinds of weird angles, we're just assuming it's one-dimensional problem, we can write it in terms of just the displacement in the x. So now we have to figure out what the force equation is with respect to the displacement. So again, we go to Hooke's law. We know that the force needed to stretch an elastic material is equal to kx. So when we place that value, or we substitute it into the equation, we have work is equal to the integral of kx with respect to x, so kx dx. And we can go even further. Since k is constant, we can take it out and just say work is equal to the constant k times whatever the integral of x dx is. And the integral of x would just be 1/2 x squared. So then we do between the x final and the x initial, we multiply all this by k, and then we can actually put the k back in and say 1/2 kx between the integral of x final or between the 2 points is equal to the work done. So the work of the spring is equal to 1/2 k x final squared, and then remember we subtracted minus 1/2 kx initial squared. Now the kx initial squared we don't have to worry about because we're assuming at the very beginning the spring was at its stretched length. So its displacement at the very beginning is 0, and then its displacement at the end is 0.03 meters. So we plug that in. So the 12 joules was able to do, and we plug in 12 joules for the work is equal to 1/2 kx, and then remember we changed the displacement from centimeters to meters, and we square that. So now we have the equation 12 joules is equal to 1/2 k times 0.03 squared, and then we can solve for k, and we find out that k is equal to 2.67 times 10 to the 4th newtons meters. Now it's really, really long because apparently this is a very, very, very hard spring to stretch. So the k constant is 2.67 times 10 to the 4th newtons meters. Now the next problem says, how much work must be done to compress the spring 4 centimeters from its unstretched length? Again, we can't use the algebra equation, we have to use the calculus equation. Now, we don't have to re-derive our equation because we can still use the equation we had from before. So how much work, for part B is find the force needed to stretch the string 0.03 meters. So we can just use our F equals K delta X. The K we found out from before still applies because we're still talking about the same material. And we multiply times the displacement, and the force needed to stretch it out 0.03 meters would be 800 newtons. Now, for the last part, we have a little bit of space here to write down the final answer. For part C, they want us to find the work if delta x is 0.04 meter. So how much work will be needed to stretch it out? So we can still use the same spring equation. This equation, if you actually want to memorize it, or if you can derive it, whichever one, is the general work equation for any elastic material that has varying forces, as long as it abides by Hooke's law. So we can use the same equation. Again, we don't have to worry about x initial because we're going to assume that it started off at its unstretched length, which would be 0 meters. So then we just plug in our work is equal to 1/2 the k, which we calculated before, that's still the same, times this final position squared, and we find out that it will take 21.36 joules to stretch the spring to 0.04 meters. We don't always have to use the integral calculus part. We can sometimes understand just by the definition. Remember, an integral is the area underneath the curve. So sometimes if they give you a graph, you can use the graph to solve it without having to rely on like integrations and derivatives. So for this question, it says a force F is applied to a 2 kilogram radio-controlled model car parallel to the x-axis as it moves along a straight track. The x component of the force varies with the x coordinate of the car, as shown in the figure below. So they gave us the mass of the car. It says calculate the work done by the force when the car moves from 0 to 3 meters. So for the solution for part A, we're trying to find the work done as it goes from 0 meters to 3 meters. Now, remember, work is equal to the integral of dx, but remember that basically means that work is the area underneath the curve of a force versus displacement graph, which is pretty much what we have here. So the area between the 0 meters and 3 meters is the answer for part A. And we can, this is an odd shape, so what we normally do is we can break it up into two easier shapes and then calculate the area of it. So we can calculate the area of this by finding the area of the triangle first, which is 1/2 base times height. So we have 1/2 2 meters times 2 newtons, base times height, plus the area of the rectangle, which is just, base times height. So which is just 1 meters as you go from 2 to 3 times 2 newtons. And the area underneath that curve is 4 newtons meters, which is the value for 4 joules. So the amount of work that was done from the 0 meters to 3 meter mark was 4 joules. For part B, they're pretty much asking us the same thing, except they're looking from the positions from the 3 meter to the 4 meter point. So we do the same thing again. We can use our graph. The area of the underneath the curve is actually 0 because it's a straight line, so no work was done because it doesn't have a height. So the work done from the 3 meter point to the 4 meter point was 0. And then for part C, they asked us, alright, find the work done from the 4 meters to the 6 meter mark. So again, we just find the area of this, which is a triangle. So we do 1/2 base times height. So the area is 1/2 the base, which went from 4 to 6, so it's 2 meters, times -1 newtons. Now we're going to get a negative area because this is the area is below the x-axis. So this is actually doing negative work because the force is pushing in the opposite way that the object is moving. So it's actually negative work is being done. And for the last part, for part D, they want us to find the total work done from the 0 meters to the 7 meters, and the total work done is just all the work added together. So we can just add up all the parts from part A, B, and C, and we find out that the total work done, the total work done was 3 joules. So sometimes if the force is varying and they give you a graph, usually they expect you to just use some geometry to find the area underneath the curve. For the next problem, we're going to have to use the actual kinetic energy and work formula, because in this problem here, they're saying a force in the positive x direction with a magnitude of, so it's changing because they're giving us the equation, 18 newtons minus 0.53 newton meters x, so is applied to a 6 kilogram box that is sitting on the horizontal frictionless surface of a frozen lake. Fx is the only horizontal force in the box. If the box is initially at rest at x equals 0, what is the speed after it has traveled 14 meters? So it seems very confusing at first, but we can calculate this by using two main formulas. The formulas we deal with is the fact that the net work is equal to the integral of the net force with respect to the x direction, and we use this because the force is changing, and luckily they gave us the equation, so we just find the integral of the force formula they gave us. And we're also going to use the equation that says net work is equal to the change in kinetic energy. That formula is the one that's going to help us associate our work to our velocity, and since change of kinetic energy is the final kinetic energy minus the initial kinetic energy, and the initial kinetic energy is 0 because the problem says that the 6 box that is sitting, which means usually implies that it was at rest, so we don't have to worry about initial. So pretty much net work is equal to the kinetic energy final. So if we can find the net work, we can find the kinetic energy final, and since net work is equal to 1/2 mv squared, and we know the mass, if we can find the net work and we know the mass, we can find the final velocity. So we need to figure out what the net work is. So basically our x final position in the x is 14 meters because it tells us it's moving from 0 to 14 meters. Our initial we set as 0. So we do our integral. We got to do the integral of that equation they gave us. So when we work on our integral, 18 becomes 18x, 0.530x, well the x becomes squared, and then we have to divide everything by 2. So that becomes our integral. So we're looking at the integral of that between the final and initial position. So when we just write down the formula, I'm just showing all the work. You obviously don't always have to show all this work because we're going to find out that things cancel out. So we get this equation. We plug in the final and subtract it by the value we get when we plug in the initial. And since the initial is 0, we don't really have to worry about that. So pretty much the net work is 18 times 14 meters minus 0.530 divided by 2 times 14 squared. And when we plug all that in, we get 200 joules. So the net work done as this object was pushed from 0 to 14 meters was 200 joules. So then we use our network again to find our final velocity using kinetic energy. And we plug in our mass that was given to us. And then we can just calculate that the final velocity was 18.17 meters per second. And that's our final answer. And that's it.